and Wilhelm Auer. Marina joined Infineon Technologies in 2020 and is currently a product marketing manager for medium voltage MOSFETs. With a master's degree in business, she is effectively bridging the gap between product development and customer needs. Wilhelm is a product marketing manager. He also joined Infineon in 2020 after earning his master's degree in electrical engineering and economics from the University of Graz. He's an international graduate program alumni and has worked in product marketing on medium voltage GaN-HEMT and silicon power MOSFETs. Following the presentation, we'll have a live Q&A with Wilhelm and another Infineon colleague, Guilherme Bueno Mariani. You can submit questions at any time during the session using the Q&A box on the right-hand side of your screen. We will provide our attendees with a downloadable copy of the presentation near the end of today's session, and the slides will be available in the Handouts tab in that upper right-hand corner. And at the end of the session, I will be announcing 2 winners of this live session's giveaway. Thank you so much for joining. With that, I'll hand it off to Marina and Wilhelm for their presentation.
Hello, hi, my name is Marina. I am Product Marketing Manager at Infineon, focusing on silicon power MOSFETs ranging from 100 to 400 volts. Thank you very much for having me. And this is my colleague.
Yeah, thank you. My name is Wilhelm Auer. I'm also working in product marketing in silicon MOSFET, power MOSFETs from 100 to 400 volts. And thank you so much for joining our webinar today, the OptiMOS 5 Linear FET 200 volt enabling optimal protection in BMS and hot swap.
Yes, thank you. So with that, I will kick it off and let's have a brief look into our agenda. We keep it really short and crisp. So first of all, we would like to give you a quick introduction, and afterwards we will really focus on the technology highlights of the 2 main focus applications, namely the BMS and the hot swap. After that, we will wrap it up in a short summary and also provide some additional material that you can use afterwards. So, and with that, let's have a quick look first into our first part, the introduction. So we have mainly within the silicon power MOSFET portfolio, we have 2 main families, namely the strong Linear FET and the OptiMOS. Where is now Linear FET 2 positioned? It's within the OptiMOS 5 Linear FET family, as you can see here, marked in blue. So let's have a quick glimpse into the overall portfolio of the Linear FET 2 in 100 volts. As you can see here, it consists of several packages starting from the tall T, so the top side cooling, the tall T top side cooling, but also the D square packs. And one of the latest additions is also the M tall G, so it's an 8x8 package. In general, all the parts are released already. The latest addition in M tall G 8x8 will be released in the next couple of months. With that portfolio, we mainly focus on 2 applications, namely the hot swap and the BMS, which of course does not mean that it's not suitable for other applications. Within our presentation today, we will really focus on the technology highlights of hot swap as well as BMS. First of all, before we go also into these details, let's have a look into the overall benefits of the technology itself. So, in principle, the first thing what is really important, especially in hot swap applications, is wide SOA. So compared to our OptiMOS 5 products, we have a 12% higher SOA and also a 3.5 higher SOA in short pulses. So as well as for long pulses and short pulses, we see significant improvements there. This, of course, helps you in harsh application conditions, such as hot swap, for instance, where MOSFETs need to handle a really high inrush current. Secondly, the RDS-on. In principle, our portfolio is positioned and consists of really low ohmic devices. However, you can even get a further RDS-on reduction if your overall system allows you a higher drive voltage to up to, let's say, from 15 or 12 volts, right? So you can really have additional RDS-on improvement of up to 13%. This, of course, results also into an overall improvement of efficiency and power density. Last but not least, the optimized transfer characteristics are also worth to mention, and we will go into really detail later on in the presentation. Overall, in the BMS application, current sharing or paralleling MOSFETs is of course a really important topic. And with Linear FET 2, we address this, we also address that with our technology. So we really have, we are focusing in our developments to focus on optimizing the features that enable and allow you a better and easier current sharing. Overall, it results into high system reliability and also, of course, power density, as the one or other part might be reduced. With that, we will focus now, as said, on the highlights of these two main applications, so the hot swap and the BMS, so the battery protection. Both applications have different challenges, different needs, different requirements, and we will focus on each of those and also show you how Linear FET 2 can help you to address these challenges. And with that, I would like to hand over to Wilhelm now.
Yeah, thank you very much, Marina, for this introduction. As mentioned, my name is Wilhelm. I'm also working in product marketing, and now we are going to go into the technology highlights and in the focusing on the battery protection socket in the battery management systems. So we took here the liberty to merge the application requirements, application description with the technology highlights to bring the improvements of the OptiMOS 5 Linear FET 2 technology to you in the most concise possible way. So let's start off with the battery management system. On the right hand side you can see a system block. It consists of the controller, the cell monitoring and also the battery protection block. In general, you have BMS or battery management systems for all lithium-ion batteries that are employed. And the job of this system is to keep the lithium-ion battery in the right operating conditions and then also perform a variety of functions, as you can see here, such as control or monitoring and sensing and so on. As far as the MOSFET is concerned, the most relevant part is the battery protection unit. So when we focus on this one, you can see here on the right hand side, the BMS connects the lithium-ion battery, which are displayed on the left hand side in these cells, with a load. And the load can here represent any type of system that you want to power with your battery. So this could either be a server or a motor or anything like that. And the main job of the battery protection unit is to connect and disconnect the battery from the load. And for this, there are certain conditions under which this has to be done. You can see some of them mentioned here, such during overcharge, deep discharge, inrush current, or also the short circuit. And the short circuit, from a MOSFET perspective, is a particularly challenging condition. The reason for this is when a short circuit occurs, very high currents are flowing through the MOSFETs, and during this time the MOSFET has to turn off to protect the system. This is its main job. And as you can see here, the currents that we're dealing here are 3 to 10 times higher than the normal on-state current, so this is a huge stress on the device. And this stress in the end results in SOA requirements that are given by the short circuit current, the VDS, and the turn-off time. Additionally, this is a critical condition for the MOSFET, because if you're not successful in turning off the MOSFET, then it will fail as a free terminal short, leaving the battery and the system unprotected and the short circuit current just running through, leading to damages. Secondly, as you can see, the battery protection unit is in the direct current path between the battery cell and the load. And this also has implications on the conduction losses and the system efficiency. So for a power MOSFET, the conduction losses are given by I square, so the current is flowing through the MOSFET, times the so-called RDS on. The RDS on is a measure that describes the on-state resistance of a MOSFET during its fully on state. And as you can see here, it goes into the multiplication with I square. So this is an important characteristic of the MOSFET that describes how efficient it is in the so-called on state. Here we can see the lower the RDS on, right? So the better it is generally, and this leads to two system implications. First of all, the battery life. So the lower the RDS on, the more battery life you can get out of a given battery. And secondly, the system efficiency, which is also important in certain cases. So, and these two give us the main two requirements for MOSFETs in these applications. And now I would like to step-by-step deep dive into these. Let's start with the safe operating area. You can see here a chart of a safe operating area of a 100-volt MOSFET device. The safe operating area is a diagram that's defined by the absolute values of the voltage and the current. You can see the current on the y-axis and the voltage on the x-axis. So any given point in this diagram is defined by these two parameters, but also by the time. So in the end, we are always thinking about a square power pulse for which we can find a point in this diagram. For battery management systems, the turn-off times that the MOSFETs are facing are dependent on the parasitic system inductance. And therefore vary widely from system to system. We already saw that there are a variety of applications that are using this battery management system, so you can expect some variation here. And this is generally in the tens of microseconds to hundreds of microseconds. And if we look here into this diagram, you can see here this is in a space where this orange line is given the limitation. And this is the so-called thermal stability limitation. And this is driven by the positive temperature coefficient, which we'll learn later on more in the transfer characteristic, that in the end leads to a hotspot formation in the MOSFET that can lead to a failure when operating outside of the SOA. As far as we are concerned for the battery protection, we want to have here as much headroom as possible to enable these system requirements we just talked about. So, and now let's have a closer look on the OptiMOS 5 Linear FET 2 technology compared to the OptiMOS 5 technology. For this comparison, we picked the 100 microsecond time frame at 54 volts as a representative condition for this application. When we compare the safe operating area between the two devices, we can see that the OptiMOS 5 Linear FET 2 provides 81 higher amps. So you go from 32 amps to 113 amps. And so in other words, you get a 3.5 times improvement compared to the OptiMOS 5. So this is quite a huge improvement. And as we've just heard in the application, this enables you to turn off higher short circuit currents, or as we will see shortly in an example, to reduce part count at the same short circuit current. Yes, and so now we've had a look at the first requirement. Let's also have a look at the second requirement, to have a low RDS on. When comparing technologies, it is useful to have a look at the type of chart that looks like this, where you have the robustness of the device and the RDS on in a chart. And what we can see here, if we look at the OptiMOS 3, this is a device with a relative good balance. So you have a relatively low RDS on for what the technology can do, with a relatively high safe operating area. When we look now at the OptiMOS 5, this is located on the left bottom side. So the RDS on is significantly reduced compared to the OptiMOS 3. However, here the safe operating area was traded off. And this is a very typical thing. So if you look across technologies, generations, typically you have to trade off some robustness in the device to get to a better performance. The OptiMOS 5 Linear FET 2 technology allows now to break this trade-off and you get a very low ohmic device with a very high SOA. And and if you look at this chart on the right hand side, you can see some comments. So you also immediately get some kind of positioning of the products. Let me mention one more thing. So we will see this one later for the OptiMOS 5 Linear FET 2. There's also, Marina mentioned it in the introduction, a trick when you increase the VGS, you can further decrease the RDS on. So here, this is not the end of line. You can get a little bit more out with some system considerations. Yeah, and let me come now to this topic, which you probably already suspected, and this is the topic of paralleling MOSFETs or current sharing. So we've already heard a lot about the safe operating area, the robustness of the device, and also the RDS on, that this has to be low in the battery protection socket. And paralleling MOSFETs here comes very natural because you can decrease your system RDS on by paralleling more and more devices. And you can also ease the burden of a single MOSFET SOA due to the short circuit condition, because in this application, the devices share the short circuit. So the more devices you put in parallel, the more robust your system becomes. However, when you're paralleling MOSFETs, there are also some challenges, and these are visualized on the right-hand side. So if we think about switching parallel MOSFETs, then we also have to think about the VGSTH, so the gate threshold voltage. And this voltage defines when a device is fully turned on and when it's fully turned off, very roughly speaking. So during production, there is a parametric spread of the VGSTH. So when you're paralleling devices, you have to assume that not all the devices have the same VGSTH, but that there is some kind of variation. And now the question is, okay, if I switch these devices with this variation, what happens to them? And here you can see the lowest VGSTH device here marked in orange. If you switch this off, as in the short circuit condition, then this device will see a higher current because it turns off latest. So it takes the highest current load, and then this can lead to in the end a hotspot in the MOSFET, right? So this is something you generally don't want in the application. And the question is, what can you do? What can you do about it? And traditionally, the only solution was to over-design the system. You just put more MOSFETs in parallel so that even in this worst condition, you're still well within the safe operating area of any MOSFET. But it would be much preferable to have a MOSFET with improved current sharing to avoid this over-design and system reliability challenge that also comes with this. And so, yeah, now we heard a lot about these conditions, and to summarize here, I wanted to give you a calculation on how does it look at a real-life example. And when we are thinking about these real-life examples in these battery protection systems, we always have to consider two main drivers that we talked about, right? The on-state current and the short circuit. So these are the two drivers of part count. And in the end, I want to minimize my part count because it enables higher power density, and also it improves my overall BOM cost. Something I have to consider when we're talking about the on-state current is also the maximum MOSFET temperature. So the MOSFET has to be operated in a certain temperature. This can also vary across applications, what is allowable here. But we made here some assumptions at an example that is very close to real life. So on the right-hand side, you can see all the system assumptions that were made. And on the left-hand side, you can see the implications on the part count. So when we start on the very left-hand side, here with our representing our OptiMOS 5 technology with the IPT015 N10N5, you can see that we get to a part count of 12 devices. And now the question, why is that? And the reason is because we have to parallel more devices to fulfill the short circuit requirement. In this case, the device is not limited by its on-state current. Here you can see 6 would be sufficient, but you have to go to 12 to fulfill your short circuit requirement. When we compare this now with our OptiMOS 5 Linear FET 2, this technology, as we heard, is much more capable in terms of SOA. You would only need 4 devices to fulfill this short circuit requirement, but you need at least 6 to fulfill the on-state current requirement. So here the device is effectively thermally limited and you get to 6 devices. But compared to OptiMOS 5, you have a 50% part count reduction, which is huge in terms of BOM cost. Also in terms of power density, you get a much more compact design. Yeah, so if you want to improve from there, then we have to improve our thermal behavior of the device. And here we also, Marina mentioned it before, we have a topside cooling device, the so-called TOL-T, in the portfolio, and this one brings along superior thermal performance, so you can push more current through a single device with an acceptable temperature, and this allows you then to go to 4 devices, so you have an additional increase, but this has a bit of a different mechanical setup. So on this, I just quickly wanted to highlight here the difference between a bottom side and the top side cooling setup, since we just talked about it. So when we're talking about the bottom side cooling setup, you can see it on the left hand side. So you have the MOSFETs, the PCB, then below a TIM, so it's a thermal interface material. This is effectively a electrically isolating material but thermally conducting material, and then a heatsink. So this would be the so-called thermal path, so the path where the heat has to follow to be dissipated in the system. On the right-hand side, you can see a topside cooling setup with our TOL-T, and this is very different. So you have the PCB, you have the MOSFET on top, but then on top of the device, you have this thermal interface material and then the heatsink. And on the system, this has a lot of implications. First of all, of course, you have a different mechanical setup, but this also translates to certain advantages. And the 2 main advantages are, since the TOL-T is an overmolded package to the bottom side, you have very little heat transfer to the PCB. This also means that the choice of your PCB has relatively little impact on the thermal performance of your device. Secondly, the TOL-T has a reduced RTH due to this improved thermal path. And this translates to about 50% higher output power when you test it, as we saw in our example before. So this is quite a huge benefit. And with that, you also get to a higher power dense device and you can push more power through the device. Yes, and now let me come to the last part here in the battery protection section of our presentation. These are the application tests. So our colleagues from the application team did here a simulation to quantify the benefit of the current sharing of the OptiMOS 5 Linear FET 2 technology compared to a normal OptiMOS 5 technology. We'll hear about the transfer characteristic a bit later in Marina's part. So, and to do this investigation, the difference in energy during the turn on and turn off event was taken between these 2 MOSFETs under test in the simulation. So this difference, so the higher the difference, the worse the current sharing of the device. So this was the measure that was selected. And a simulation is quite a nice tool to quantify this type of characteristic of a MOSFET, because you can sweep through certain parameters. So here you can see the delta VTH in percent, which is the difference of the VGSTH between the 2 devices, and this is here in percent. So if you go to 100%, this is the maximum distribution that you would find in the datasheet. If you go to 0, then this is perfect current sharing. When we are comparing now these 2 devices, you can see the green line is going in this arc much higher up than the OptiMOS 5 Linear FET 2. And in this graph, you can see that the OptiMOS 5 Linear FET 2 provides up to 64% better energy distribution while current sharing. So this is quite a big advantage. Let me also mention here that this advantage increases with the amount of devices paralleled. So the more devices you parallel, the bigger the advantage of the OptiMOS 5 Linear FET 2 technology will be when it comes to current sharing. Yes, and not only simulations have been done, but also bench testing. Here on the left-hand side, you can see the setup where the bench testing was done. And the idea of this bench test was to test the device in as close to application environment as possible. So devices were effectively tested in a turn-off test, also operated outside of the SOA, so you can really see what the devices can do and when they would fail. And then these results were combined with the battery simulation, a model that was done before, and results then in the chart on the bottom left-hand side that you can see. So on the time scale, you have here in microseconds. On the x-axis and on the y-axis, you have the maximum current that was successfully turned off by these devices, adjusted for the current sharing. So effectively, you're considering two devices. What we can see here is that, unsurprisingly, the OptiMOS 5 Linear FET 2 can turn off much higher short currents than the OptiMOS 5 technology. Here specifically 2 times higher compared to the OptiMOS 5. And then when we go to these two devices, in considering also the current sharing, this advantage increases to 2.5x. So this is quite a big advantage. Yeah, and with that, thank you very much for staying tuned for our BMS part, and we'll now hand over to Marina for the hot swap part of our presentation.
Yeah, thanks, Wilhelm. So as already teasered, we will now focus on the technology highlights within the hot swap applications. All right, so let's focus first on the functions of a hot swap and also the challenges itself. So hot swapping is in principle a technique that allows, of course, a device to be removed and replaced with one another without any disruption in the normal operation of the system. So even if you remove or add parts, the overall functionality remains and it continues to run smoothly. So now every time when a device, for instance, a server blade is added, then it has an input filter capacitor that is discharged at the time of plug-in. What does that mean? It means that this results in a really high inrush current, and potentially it can occur that some failures in the systems are observed. That's why our MOSFETs, or in general MOSFETs that are placed as a hot swap MOSFET, need to be able to handle high inrush currents in order to also, in order that this risk, so to say, of potential failure does not occur. Where in principle our MOSFET is located is it's located between the back plane, so in the direct current plane of the back plane and the load. So that's why also low ohmic devices are super crucial here. So let's have a look into the wide SOA. Wilhelm already explained what an SOA in general is about. So it's in principle the region where the device can operate safely without risking any damage or failure. So it's defined by the maximum allowed current, voltage, and power. And especially if we look into the hot swap application, for instance, the timing of 10 milliseconds and longer pulses is super crucial. We did now a benchmark comparison, also took a look also on the best next alternative. And as you can see here depicted on the right-hand side, our IPM 018, so it's the MTOL G8x8 package, is able to handle 14 amps at 50 volts within this 10 milliseconds. And this shows you an improvement compared to the best next alternative. Also, when we look at the RDS on, we have also here an improvement of roughly, let's say, 17 to 20%. So it's 1.85 milliohm. So now let's have a look also in how we compare the SOA performance compared to our predecessor, so the Linear FET. You also can see here that we have a 1.8 times improvement in SOA, also at 10 milliseconds at 50 volts. And overall, this really helps you to, so to say, to enable this overcurrent protection of systems. So, and with that, let's have a look at the second most important benefit in that sense, which is the RDS-on. In principle, as already teasered, our entire portfolio of the Linear FET 2 in 100 volts is positioned with really low ohmic devices. But you can, so you see in this chart, the RDS-on on the y-axis and the VGS on the x-axis. And this curve becomes really, really steep if you go below 10 volts VGS. So it's not really recommended to drive this device below this voltage. However, if your system allows you to also increase your driving voltage from, let's say, 10 to 12 or 15 volts, this gives you a huge improvement in RDS-on of up to 13%. So that's really a significant reduction. And if we compare it with our OptiMOS 5, so the IPTO15, so it's the tall package, then we are here on par with our, so to say, classic OptiMOS 5 MOSFET. Yeah. And now, last but not least, as also teased already by Wilhelm, let's also have a look into the optimized transfer characteristics. So on the left-hand side in the chart, you see the OptiMOS 5, also the comparison with the tall. And on the right-hand side, we see our Linear FET 2. So the OptiMOS 5, Linear FET 2 in 100 volts, also in the same package in the tall. So the line, so we go now step by step because it's a lot on the slides, but I will lead you now step by step through this slide. So the line in ocean is depicted here in green or in this bluish color, whereas it's the 175-degree line, and the line in gray is, so to say, the 25-degree line. So it shows you, we can observe in that sense really the following differences, let's say. So let's have a look first at the zero temperature coefficient point. So below this zero temperature coefficient point, in principle, the MOSFET has an unstable operation. So of course, you want to have this zero temperature coefficient point as low as possible. So compared to our OptiMOS 5 part, we have with the Linear FET part, this line is much lower. So you see here, it's depicted on the right-hand side. And this, what result does that have, right? It's which means that it's overall this lower zero temperature coefficient point. With that, you have a lower chance of thermal runaway. And ultimately, it also, of course, impacts the wide SOA, so the SOA performance. Another key difference is also the GFS. So we have here, with our Linear FET 2 technology, really a low transconductance, so low GFS. We came from, so it was 140 Siemens for the OptiMOS 5 and only 80 Siemens for the Linear FET 2, which is also, of course, a significant improvement in that sense. This results into a lower ID sensitivity in that sense, and also helps you when paralleling multiple MOSFETs. Last but not least, of course, also the within the one of the challenges is, as mentioned, the high ID sensitivity of VGS during startup. As you can see here, depicted in the number 3, we have a much lower current at 5 volts, which of course helps you exactly in the startup phase within the hot swap application. So I hope that I could give you a quick glimpse on the key benefits in this application. And now this is already the last part of our presentation. So beyond what we can offer here from the parts point of view, we also have hot swap demo boards as well as evaluation boards that we developed during our project. This, of course, helps you also to test. These are, of course, also orderable, so you can order these and also test the one or other condition with our evaluation boards as well as the demo boards. This presentation is also shared afterwards, so please feel free to also dig into the details and read all the parameters and all the technical details in that sense. So if we now, I will click it. So now looking at the key features and key takeaways of our OptiMOS 5 Linear FET 2 in 100 volts, it really has a low RDS on, and we can even further decrease the RDS on, right? As we have learned. We have a wide SOA that helps you really in long as well as short pulses, which is super crucial and vital for both applications, the hot swap and the BMS. And with our Linear FET 2, we really try to optimize here the way that it allows you a better current sharing. So if paralleling multiple MOSFETs, Linear FET 2 technology will help you to do that. Yes, and I think all the rest has been mentioned quite in high detail. Thank you very much for listening. We have, of course, some material that is published already on our website. So please check out our website. And we have introduction videos and all different kind of application notes. So please check out the material there. And with that, I would like to open the floor for any questions. And me and Wilhelm are happy to answer these. Thank you so much for listening.
All right. Well, thank you. Thank you, Marina and Wilhelm, for that really great presentation on circuit protection. We already have several interesting questions, but I want to let our audience know that there's still time to submit your questions. Use that Q&A box on the upper right-hand side of your screen. Wilhelm and Guilherme, are you ready to answer some of these questions?
Yes, we are. Yeah.
All right. So our first one is asking, is OptiMOS 5 Linear FET 2 also suitable for other applications?
Yes, I can take this one. Yeah. So